Most people don't fail when building their own generator because they lack effort. They fail because the system behaves very differently than expected. At the beginning, the idea feels straightforward. Convert motion into electricity. Spin something, generate power. It seems almost mechanical in its simplicity. And that's exactly what draws people in. So the process starts. You gather materials. Magnets, coils, maybe a motor. You watch tutorials. You follow diagrams. Everything appears logical: input motion, output electricity. And in the early stages, it even works. A small light turns on. A meter shows voltage. There's proof that something is happening. And that moment creates a surge of confidence. It feels like you're close. But then comes the next step: scaling. Because producing a small amount of electricity is one thing. Producing usable, stable power is something else entirely. You try to increase output. Spin faster. Add more coils. Improve the setup. But the results don't scale the way you expect. The effort increases, but the output doesn't follow proportionally. That's where the frustration begins. Because logically, it feels like more input should lead to more output. But instead, new problems start appearing. Heat builds up. Resistance increases. Components become unstable. Energy losses start stacking in ways that weren't obvious before. And suddenly, what looked simple starts to feel unpredictable. At this point, most explanations stay at the surface. You need better materials. You need stronger magnets. You need a more efficient design. All partially true, but incomplete. Because the real shift happens when you move beyond the visible components, and start looking at the structure of the system itself. A generator isn't just a device that creates electricity. It's a system that converts energy, and every conversion comes with trade-offs. Mechanical resistance turns into heat. Electrical resistance reduces output. Magnetic interactions create drag. Every part of the system pushes back in some way. And those small inefficiencies compound. That's why scaling feels so difficult. Not because the idea is wrong, but because the hidden costs grow faster than expected. The real issue isn't building a generator. It's expecting linear results from a non-linear system. Once you see that, things start to make more sense. Instead of asking, why isn't this producing more power, the question becomes, where is energy being lost in this system? And that question changes everything. Because now, you start noticing details that were invisible before. Friction points, heat dissipation, electrical resistance, load imbalance, energy that never makes it to the output. And more importantly, you start understanding why small demonstrations can be misleading. A tiny setup can look efficient because the losses are minimal at that scale. But as soon as you try to extract meaningful power, those losses expand rapidly. That's the turning point. Because it shifts the goal from making it work to understanding why it behaves this way. And that understanding is what separates curiosity from control. From there, the perspective expands. You begin to see that real-world power systems aren't just bigger versions of small DIY setups. They're engineered to manage loss, stabilize output, and handle variation over time. They account for variables that aren't obvious in a simple build. And that's why replicating them isn't just about copying a DSIG, it's about understanding the structure behind it. This doesn't make DIY generators useless. It makes them educational. They reveal how energy actually behaves when you try to control it. They expose the gap between theory and application. And they show why generating power at scale requires more than just assembling parts. So instead of focusing on whether a homemade generator can work, it becomes more useful to ask what it teaches. Where energy is lost, how systems respond under load, why output doesn't scale the way we expect. Those insights are far more valuable than a temporary result. Because once you understand those patterns, you can look at any energy system, simple or complex, with a completely different lens. If you want to go deeper into that, there's a structured breakdown in the description that explores how to analyze these systems step by step. And if you're interested in understanding how real-world energy systems are designed and why they behave the way they do, you can subscribe for more grounded, technical explorations like this.